Hi everyone. So today I will present you the GPU architectural benchmarking for ML-based Algae instance segmentation. I worked on with my manager Mauricio here, and also in collaboration with Bruno Conche, which is responsible of the project in Pau in France. So as you already know, this is to say that all the results I will present you are results that are matching with my use case, and you shouldn't use that as a financial decision. So, quick introduction about myself. As you can hear from my accent, I'm from France, and I studied in General Engineering School in Paris. During my studies, I also worked as software engineer for a startup, and also as data scientist for a consultancy company. I got my master's degree in 2021, and then I moved to Norway for 2 years to work as computer vision engineer for a startup working in wind industry. And then I joined Total Energies here in Houston 6 months ago to work as machine learning researcher. So, quick agenda for today. First, I will explain you the motivation of the project, which is about monitoring spirulina while consuming CO2. I will give a short introduction to the computer vision task for people that are not really familiar with that. Then I will explain why we need machine learning for this project and why we need HPC. And then I will introduce which machine learning approach we chose. And then I will go deep in the benchmarking part about the model training and the model inference. And then I will end up with some conclusion on the future work. So, as everyone knows, we are in a pretty critical situation about global warming. And so the COP28 fixed a goal about cutting the CO2 emission by 43% by 2030. So how can we reach this goal? So one of the possible solutions is what we call CCUS, carbon capture, utilization and storage. So how can we capture this CO2? There is one method that is based on algae culture that are capturing CO2 that has demonstrated previous interesting results. And the idea is to use these algae that are capturing CO2 to then create biofuel. So to give you a little bit more context of the project, I wanted to add a picture of the tank where we have the algae culture. So this is one of the examples, and this is where we are collecting the data. So with a little machine, we are capturing images. And then with the microscope, we connect that to a computer, and this is where we can do the monitoring of the algae culture. So the goal is to monitor this culture of the spirulina. So spirulina is one type of algae that has good properties for CO2 absorption. So this is one sample of the images we are getting from the microscope, which is about 1,600 by 1,200 pixels. So you can see like some algae here, the straight lines. And this is what we got after doing the algorithm. So what we want to be able to do is to automatically detect the algae in the picture. We also want to be able to classify them, because there are actually two types of spirulina. One that is straight and one that is curved. And they have different properties in terms of CO2 absorption. And we also want to be able to segment the algae in the picture, because we want to count the dry material. And so the idea at the end is that to observe if, for example, we change one parameter such as temperature or light, how the algae culture is reacting to that. So the question for this project was, what is the best hardware-software combination we can use to implement this solution? So two questions are coming from that. How can we optimize the model training? and how can we optimize the model inference in order to process the data on site in real time. But so maybe you are wondering, why do we need machine learning for that? Because maybe you know that there are some traditional image segmentation methods that we can use. So I added some here. I don't want to go into the details. I just want to show like two main ones, which is thresholding and edge detection, which are two different methods that you can use and that are pretty fast to do some image segmentation. The only problem with those methods is that you need to set by yourself some parameters. You need to hardcode some parameters. And so for each type of image, you will have to find the correct parameter. So it's not really scalable, and the quality sometimes is pretty poor of the result. So that's why we moved to the deep learning-based method, which are able, so it's a model that you will train and that will set by themselves the parameters, and you can get a good quality for the object detection, the classification, and the segmentation. So I just mentioned two main ones, which are mask or CNN, which is a convolutional layer model. And you also have YOLO, which stands for you only look once. That are the two famous ones nowadays. And with them, you are getting a way better quality, and it's way more scalable for diversity of images. So just quick introduction about the main computer vision task, so everyone knows what we are speaking about. The simplest one is image classification. You give an image to the model, and you want the model to say what the image is. Like, is it a cat, is it a dog, or whatever. Then you can go even further and classify what objects are in the image and draw a bounding box around them, so find the location of these objects. And you can go even further with what we call instance segmentation. So it's kind of the same as object detection, but you will also find the contours of all the objects. And this is the case for the project because we want to be able to count the dry material for the algae. Okay, so which machine learning approach did we choose for this project? We decided to go for the YOLO V8 algorithm. So I don't want to go too much into the details of the algorithm, but I want to explain you why we need HPC for that one. So basically, as YOLO say, you only look once. It will only do one step to figure out all the instance segmentation on the image. So as you can see, what it does is it will create a grid on the image, and it will find the objects, try to draw some bounding boxes around the objects, and then we'll construct the image, and it will give some bounding boxes with some confidence scores. Plus, it will also give a class probability map, so to give you what type of objects are in the bounding boxes. Then there is another step that we call non-max suppression, that we remove all the unnecessary bounding boxes to end up with the nice result of the bounding box around your objects. And for instance segmentation, there is just an extra step to find the contours around the object. So, and YOLO is based on convolutional layers, which are basically matrix multiplications. So it's really well adapted for GPUs optimization. So that's why if you want to have an efficient model training, you need GPUs and you need HPC. That can be done on-premise or in the cloud. So now I will enter into the training phase. So to give you a quick overview about my setup, I worked with 4 devices. I worked with NVIDIA A100, NVIDIA H100, Tesla T4, and NVIDIA GH200. About the software, as I mentioned, I'm working with YOLO V8. About the data set, I got samples about 3,000 images to train and 100 images to test. So I think you will say, oh, this is a really tiny data set. But in real use cases, it's tough to get images. So we are currently getting more images, but you need also to label them with some experts. So that's why it's taking time. But the idea then is to train the model with a way larger data set. So actually, what does it mean? Training a model. So training a model is just an iterative process where you will show some images to the model. It will try to do some predictions, and it will compare with the real labels, and it will calculate what we call an error, and that's what we can see here on the loss function. So over iterations, like epochs, you want this loss function to decrease. So you want your accuracy to increase. And during your model training, there are some important things to look at, such as your research usage. Are you correctly using the resources of your device? Also, the energy consumption is an important parameter to look at. Also, the input dimension of your image can have an impact both on performance and accuracy. And then also, you need to check about your I/O performance. Is there an I/O bottleneck that will slow down the training or not? And also, you need to still set by yourself some parameters. So you need to find the best combination possible. That's what we call hyperparameter tuning. OK, so now I want to show you the results working with only one GPU for the 4 devices I was mentioning. So I was working with a batch size of 16 images per iteration, which was representing 12 gigabytes. I was training for 500 epochs iteration using YOLO V8. And everything is based on Torch Vision, which is based on Torch, which is based on CUDA-NN, which is based on CUDA, which is using Python. And I was using Python 3.8. So this is the graph of the evolution of the training for each devices. Maybe we don't see that much, so I tried to sum up that in a table. So each row corresponds to one device. For each device, you have the total training time, the final precision, the best precision, when did we reach the best precision, the total energy consumption, and the price of each device. So as you can see on H100, it was taking about 7.5 hours, 11 hours on A100, 11.5 hours on GH200, 23 hours on T4. And about the precision, it was pretty equivalent, I would say. And about the energy consumption, T4 was the one using less energy, but it was also the slowest one. So it's always a trade-off between price, time to train, and precision. So when I did this experiment, I wanted to speed up even more the training. So I wanted to parallelize the training using multiple GPUs. I decided to work with A100 because this is the one that we are working more with currently. And so I did the same experiment working with 1 A100, 2 A100, and 4 A100. And this is the result I was getting. So again, I did a table, which is, I think, easier to understand. So there is a time to train the best precision and the time to reach the best precision. So as you can see, from 1 GPU to 4 GPU, we divided by almost 5 times, more than 5 times the training, without any degradation in terms of precision. So once I had that, I wanted also to check what about the energy consumption. So I recorded the power consumption, for 1 GPU and 4 GPUs. And I did some calculation, and actually for the energy consumption, it was using even less energy training with 4 GPUs because of the faster training. So then I just wanted to check a little bit about the resource usage for 1 GPU and 4 GPUs. So I was looking at the GPU utilization, and actually I figured out something pretty interesting, is that with 1 GPU, there was some dropping in terms of GPU utilization. So you see sometimes it's like getting lower than 20%, whereas in the 4-GPU mode, it was always more than 80%. So I didn't have that much time to investigate this thing. I did some profiling with Nsight, and I figured out that in 1-GPU mode, sometimes it was using almost 50% of the time for the memory. But yeah, we need to do some more investigation to understand the root cause. But so the idea is that the I/O utilization is pretty critical when you train a model. Then I wanted to look at the batch size. How can I speed up even more the training, just changing the batch size? Is it decreasing the precision? So I worked with 4A100, still for 500 epochs. And I worked with a batch size of 8, 16, 32, 64, and 208, which was the maximum I was able to fit in memory. Again, I sum up all of that in a table. And actually, you can see that going from a batch size of 8 to 208, we were able to divide by more than half the training time per epoch without decreasing the precision. Okay, so now we are happy, we have our trained model. We want to test inference. We want to test, if we put that in production, how will it look like? So you just need to load your trained model, to run some inference on images, and evaluate the performance. So for this test, I worked with 7 different devices. I worked with A100, MI100, NVIDIA Jetson Xavier, which is an edge device. We also worked with the M1 chip because it's something that is available in the lab for this use case. NVIDIA H100, GH200, and also Tesla T4. So there are 3 different formats that you can use to export your model. You have the Python one, the Onyx one, and TensorRT. So in this graph, you can see for each different device how much time it was taking for each different model format. And I was also testing on CPUs and GPUs. So again, I sum up all of that in an array. For each device, you have one row for each device, and you have the fastest inference in milliseconds. You have also the power consumption in watts, and the price of each device. So for that, I will say that it's always a trade-off between cost, precision, and speed, right? So for example, if you need something that will run really fast, you can go for the H100 that was taking 6 seconds, but it's consuming a lot of power. So for example, in our case, we were having a really low power access. That's why we were interested to look at the Jetson Xavier, which is an edge device, and which is consuming way less power. So maybe you can tell me, oh, but the Jetson Xavier is the one with the longest inference time. But if you think about it, like 100 milliseconds means that you can process 10 images in 1 second, which is way more faster than a human can do in 1 second. So it's actually already really helpful. And about conclusion and future work, I would say that my conclusion is that, yes, we can scale the machine learning training on HPC resources, but it's always with a trade-off between speed, precision, cost, and energy consumption. And about the model inference, I think what was pretty interesting in this use case is to be able to train a model on HPC sphere and move it to an edge device for a real use case. About some future work, if you want to still improve your inference time without changing the device, because maybe you have a restricted access to devices, then you can try to compress the model, cutting some nodes. You can also try to use some low precision. That usually will faster the inference, but you have to also check the accuracy. And also, what would be interesting is to try some other machine learning approaches. There is just YOLO v9 that just went out. That could be also interesting to test. And there are also other alternatives that can be tested on. So, merci.
Thank you, Charlene. Excellent talk. Any questions?
Great conversation, great stuff. When you did the scaling from 1 GPU to 4 GPUs, were they 4 independent systems or were they 4 GPUs in the same system?
It was on the same node, yeah.
So one of the things in terms of that, the I/O pieces is a lot of the NVIDIA libraries do shared memory on those if they're connected with NVLink, and so that may be another place to investigate for the low amount of, or the higher utilization for GPUs.
Yeah, of course, yeah. Thank you.
Thank you.
Mm-hmm.
Nice talk, thank you. I was very interested in seeing how the numbers between the H100 and the Grace Hopper 200. I guess the Grace Hopper 200 also has an H100 on it.
Yeah.
So do you have a different algorithm that's running on the H100, which is just using GPUs, whereas on the GH200, are you using CPU, GPU, which is why the numbers are different?
No, so actually, we were also surprised about the result because we were expecting better result on GH200. So we have some, it's a really brand new device, and we are thinking maybe the framework is still not optimized for it. So for GH200, I was actually using the Docker container with the optimized library combination. So yeah, I think maybe the framework is still not optimized. Also, you have 2 chips, so maybe there's some data movement that is slowing down the process. Yeah, we need to do more investigation on this one.
Thank you.
Okay, well, that's it. Thank you so much.
Thank you.